Hey everyone, welcome back to the series. Today, we're taking a really important step. We're going to compile and upload our bare metal C code to the Arduino Due. First, we're doing everything manually. I'll type each command one by one, and we'll break down every single flag so you actually understand what's happening. So yeah, this is where things start to feel real. Let's get started. Alright, so first I'm going to compile our blink.c file, and here's the command to do that. arm-none-eabi-gcc. This is our ARM cross compiler. Now I'll tell it which CPU we're targeting. -mcpu equals Cortex-M3. Next, -mthumb. Cortex-M processors use the thumb instruction set, so we enable that explicitly. The thumb instruction set is basically a smaller, compressed version of the standard ARM instruction set. ARM processors have two main modes for instructions, ARM and thumb. ARM mode uses 32-bit instructions. They are powerful and flexible, but they take more memory. Thumb mode uses mostly 16-bit instructions, which are smaller. That means your code takes less flash memory, and sometimes it can even run faster because smaller instructions fit better in the CPU's instruction cache. Now, -0. That means no optimization. I'm keeping it simple for now, easier to debug, easier to understand what's going on. Then, -w all. Always enable warnings. Trust me, warnings save lives in embedded systems. Now, two very important flags. Here's the first one, -f ffreestanding. This tells the compiler we're in a bare metal environment. No operating system, no assumptions about the hosted environment. And the next one is -no-std-lib. This prevents GCC from automatically linking the standard C library. On a microcontroller like this, we control everything, including startup code. Now, I'll add -c blink.c. The -c means compile only, don't link yet. And finally, -o blink.o. That just says the output file name. Once we compile with -c, the compiler gives us an object file. That's basically our C code turned into machine code, but not yet a full program. Think of it like a Lego piece. It's ready to be combined with other pieces to make the final program that actually runs on the Arduino Due. Alright, let's copy this command, paste it into the console, and hit enter. And there we go, our first object file is created, blink.o. Alright, now I'm going to compile our startup.c file. Let's copy the command, paste it into the terminal, hit enter. And now we're going to link everything together. We have our two object files, startup.o and blink.o. And now we're turning them into one complete executable. Here's the command. First part, nothing new, arm-none-eabi-gcc. Again, -mcpu equals Cortex-M3 and -mthumb, still keeping -o0, -wall, -f freestanding, -no-std-lib. Even during linking, we stay in a full bare metal mode. Now, this is important. -t sam3x8e.ld. Without this file, the linker has no idea how to place the program inside the microcontroller's memory map. Then the object files, startup.o and blink.o. Now this part is new and very useful. -wl, comma, -map equals blink.map. This tells GCC, hey, pass this option to the linker. That's what -wl means, pass to linker. And -map equals blink.map tells the linker to generate a map file. The map file shows memory usage, section sizes, where every symbol is placed, and exact addresses in flash and RAM. This is gold in embedded development. If something overflows memory, if something lands in the wrong section, the map file tells you everything. And finally, -o blink.elf. This creates our final ELF executable. Okay, let's run this command. This file now contains machine code, vector table, memory layout, and debug information. It's a complete firmware image, ready to be converted into binary and flashed. And now, I'm going to convert our ELF file into a raw binary file. First, arm-none-eabi-gcc copy. This is a utility that comes with the ARM toolchain. It doesn't compile, it doesn't link, it simply copies and converts object file formats. And -o binary. The -o, capital O, means output format, and binary tells obj copy, strip everything away, and give me a raw machine code only. Because remember, our blink.elf file contains debug information, section metadata, symbol tables, and memory layout info. But when we flash a microcontroller like the ATSAM3X8E, it doesn't care about debug info. It just needs pure bytes to write into flash memory. Then blink.elf. This is our input file, the fully linked executable. And finally, blink.bin. This is the output file, a raw binary image. No headers, no metadata, just machine instructions exactly how they live in flash. And this blink.bin file is what will actually flash onto the board. Let's copy this command, paste it into the terminal, hit enter. And there we go, blink.bin is ready. Now we officially have a flashable firmware image. Okay, let's upload our binary to the Arduino Due. And here's the command. BOSAC. This is the official Atmel command line tool for flashing some microcontrollers. It communicates with the board over USB and writes your firmware into flash. Next, -i. This prints information about the board, chip ID, bootloader version, and so on. It's a good check to make sure the board is connected. And -b COM9. This tells BOSAC which serial port to use. On Windows, your Arduino shows up on a COM port, in this case COM9. On Mac or Linux, it will like this, or similar. Now, -e. This erases the flash memory and the chip before writing. Then -w. And this tells BOSAC to write the binary file we give it. And next, -v. This is for verify. After writing, BOSAC double checks the flash content matches our blink.bin. And next, -b blink.bin. This specifies the binary file to flash. Finally, -r. This attempts to reset the board after flashing. In most cases, the Arduino Due restarts and should run your new program. However, due to timing or bootloader behavior, sometimes the MCU doesn't start immediately. If your program doesn't run right away, just press the reset button manually. That will guarantee it starts from the new firmware. Alright, let's copy this command, paste it into the terminal, hit enter, and boom! If all goes well, your LED should start blinking. Alright, now we're going to create a Makefile. First, create a file and name it Makefile. No extension. Inside the file, we start by defining our toolchain, basically telling Make which programs to use to compile and convert our code. Next, we define our compiler flags. And we list all the object files our program will need. Now we'll tell Make what to build by default when we just type make. And we need a rule to turn any .c file into a .o object file. Here, the percentage sign is a wildcard. It matches any C file and tells Make to create a corresponding .o file. $< is the input file, and $@ is the output file. Now we're going to tell Make how to link our all object files into a full firmware image. This line says to make blink.elf, we need all the object files in objs and the linker script sam3x8e.ld. Alright, now let's actually run the compiler to link everything into our ELF file. Here, $@ is our target, the output file, which in this case is blink.elf. Next, we're going to convert our ELF file into a raw binary file that we can actually flash onto the board. And then we're going to create a rule to upload the firmware to the board. So now, instead of typing that long flashing command manually, you just type make upload. And finally, let's add a rule to clean everything up and start fresh. This creates a target called clean, so when you type make clean, it runs this command. del/q is a Windows command. del stands for delete, and /q is quiet mode, meaning don't ask for confirmation. Okay, now our Makefile is ready to use. But remember, we already compiled everything manually. We created object files, the ELF file, and the binary, all of it. So before we rebuild the project using Make, first we need to get rid of those generated files. We want a completely clean state, so first we clean. In the terminal we type make clean. Hit enter. And as you just saw, all the files we generated earlier are gone. And now that the project is completely clean, let's rebuild everything. In the terminal we simply type make. And just like that, the entire firmware is rebuilt. Now let's flash it. Type make upload. The LED on the Arduino Due starts blinking again. Alright, let's modify the behavior a little bit. Right now, our LED blinks evenly 500 milliseconds on, 500 milliseconds off. But let's make it a little more interesting. Inside our while loop, we currently have this. Now I'm going to change it to this. The LED will now stay on for 1500 milliseconds and stay off for 500 milliseconds. That means longer on time. Alright, save the file. In the terminal we type make clean, make upload. And now look at the Arduino Due. In the next video, we're getting started with assembly. We're going to make the board blink again, but this time writing pure ARM instructions for the Cortex-M3. It's going to take a few videos, and it's going to take us much deeper. So if you really want to understand what's happening under the hood, make sure you don't miss it. Subscribe, and I'll see you in the next one.